I'm pleased to present you the results of my work entitled Phenology and Growth Plasticity under Climatic Variation in a Short-Lived Chameleon. So, cold-blooded animals such as reptiles are vulnerable to climate change given their temperature-sensitive physiology. In fact, they rely on ambient environmental temperatures to maintain critical physiological processes such as growth, mating, or breeding. Yet, the risks facing these large, important groups, particularly chameleons, remain understudied. And in my research, I aim at understanding how chameleons may shift the timing of key events in their life cycle, also called phenology, in response to climate disturbances, and how it may interact with other life history parameters, such as growth. And the biological model chosen was Labort's chameleon of Furcifer laborti. It's a vulnerable chameleon restricted to remaining forest patches in western and southwestern Madagascar. And it provides a great model for the current study, given its unusual annual life history. Let me explain. So the entire population of the species is represented as eggs during winter, and then they hatch synchronously when the rainy season starts, and it's followed by an extremely fast growth that gives adults in less than 2 months after hatching. And so the entire population consists of a single synchronous age cohort. And moreover, this species has a short lifespan of 4 to 9 months, which facilitates the observation of whole generations. And with its compressed lifespan, any perturbations in timing would significantly reduce the time window available for growth and reproduction.
Sorry to interrupt, Miary. Could you share your screen?
I'm not sharing this. Okay, sorry.
Yeah.
I'm sorry, my bad.
No worries.
Do you want me to start again, or?
I think maybe start from your second slide, or I think the intro was pretty good.
Okay. Can you see my screen now?
Yes.
Oh, okay. Okay. Yeah, so these are just some illustrations. And this is my biological model for Furcifer laborti. And to sample the chameleons, we conducted nocturnal surveys over 2013 to 2018 in Kirindi Center of Dry Forest, which is located in western Madagascar, and where temperature and precipitation shift have already been provided. And for each individual of Furcifer laborti observed, the age class, sex, and snot vent length, or SVL, were recorded. And climate data, temperature and precipitation were also gathered. And what did we find? So we found a climate-dependent variation in the hatching time of Furcifer laborti. So as you can see in the figure, hatching always occurred after the first rains and varied by up to 1 month between years. Moreover, delayed hatching resulted in a shortening of the period between the first rains and the first hatching. And to examine the interaction of hatching time variation and growth, we estimated a juvenile growth rate by fitting SVL on time, represented by the day since the observation date of the first hatchlings. And we did that for each year's cohort. And we found that significant variation in hatching time resulted in difference in juvenile growth rate, as post-hatching growth, as a faster post-hatching growth was observed in the late hatchers. Therefore, climatic and climatic variation was associated with phenological and growth plasticity in the life cycle of Furcifer laborti. And implications for conservation are clear because complete populations could be lost if a single cohort of this species cannot respond effectively to increasing climatic fluctuations. Nevertheless, the study period is still too short, so these are still preliminary results, and we need a long-term study to provide results that would be more conclusive. And I would like to thank Dr. Eckhart and Dr. Rice, who are the co-authors of this manuscript, which is still in progress, and also the Deutsches Primatenzentrum and the Association VAG, which provided funds to carry out the field work. And this ends my presentation. Thank you so much for your attention.